Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today, we're going to cover Chapter 4 for our MCAT Organic Chemistry playlist, and this chapter is titled Analyzing Organic Reactions. In this chapter, we will cover the following objectives. We'll begin with acids and bases, focusing on their definitions, how we classify their strength, and some common functional groups involved in acid-base chemistry. Then we'll move on to nucleophiles, electrophiles, and leaving groups. We're going to define these terms, explore their properties, and examine how they participate in nucleophilic substitution reactions. After that, we will discuss oxidation-reduction reactions, where we will introduce oxidizing and reducing agents, and analyze how electrons are transferred in these reactions. We will then move on to chemoselectivity. Here we will explore how reactive locations in a molecule influence chemical reactions and how steric protection can affect selectivity. Finally, we're going to wrap up with some problem-solving strategies that can help approach reaction-based questions more systematically. Let's go ahead and get started. Our first objective is again acids and bases. There are two main definitions of acids and bases that are commonly used in organic chemistry: the Bronsted-Lowry definition and the Lewis definition. The Bronsted-Lowry definition describes an acid as a species that donates a proton, or in other words, a hydrogen ion. It describes a base as a species that accepts a proton. This definition focuses on proton transfer, and it's useful in many acid-base reactions that we're going to encounter. For example, when a Bronsted-Lowry acid donates a proton to water, it forms hydronium ions and its conjugate base. Similarly, when a Bronsted-Lowry base accepts a proton, it forms its conjugate acid along with hydroxide ions in solution. On the other hand, the Lewis definition describes acids and bases in terms of electron pairs. A Lewis acid is an electron pair acceptor, while a Lewis base is an electron pair donor. This definition broadens the scope of acid-base chemistry beyond just proton transfer. For example, when a Lewis acid reacts with a Lewis base, what happens here is they form a coordinate covalent bond, where both electrons in the bond originate from the Lewis base. This type of interaction is especially relevant in many organic reactions, especially those involving metal catalysts or electrophilic species. Then to quantify acid strength, we use the acid dissociation constant, Ka, which describes the extent to which an acid donates a proton in solution. For an acid dissociation reaction, like the one you see here, the equilibrium expression, Ka, is equal to the concentration of the products multiplied together divided by the concentration of the reactants multiplied together. Please note that liquids and solids are not included in the equilibrium expression. Now, a larger value of Ka indicates a stronger acid because more of the acid dissociates into ions, and that increases the concentration of hydronium ions in solution. But to simplify comparisons, we define the pKa, and the pKa is just the negative log of the Ka value. With this definition of pKa, we have a different reference frame for strong and weak acids. A lower pKa value corresponds to a stronger acid, while a higher pKa value corresponds to a weaker acid. This relationship is useful for predicting acid-base behavior in organic molecules, particularly in reactions where proton transfer plays a key role. Now that we've established the concepts of acids and bases, let's take a closer look at how acidity varies across different functional groups. The pKa values of a molecule provide a direct measure of its acidity, with lower pKa values indicating stronger acids and higher pKa values indicating weaker acids. This also means that the conjugate base of a strong acid will be weak, whereas the conjugate base of a weak acid will be strong. So there's this inverse relationship that's present. Understanding these trends is going to be super important for predicting reaction mechanisms and proton transfer events in organic chemistry. Let's start by examining the functional groups with the highest pKa values, which correspond to the weakest acids and the strongest conjugate bases. Alkanes have extremely high pKa of around 50, meaning they are very poor proton donors. Their conjugate bases are highly unstable, so they make for strong bases. Then, moving slightly down the scale, alkenes have a pKa of about 43, meaning they're still weak acids, but slightly more acidic than alkanes. Their conjugate bases are also highly reactive, and they make strong conjugate bases. Similarly, molecular hydrogen has a pKa of 42, indicating that it is also a very weak acid. Next, we have amines, such as ammonia, with a pKa of around 35. While still a weak acid, amines are more acidic than alkanes and alkenes. The conjugate base of an amine is called an amide ion, and it is a strong base that is frequently used in organic synthesis. We're going to see it a lot in later chapters. Moving further down, we have alkynes, which contain a carbon-carbon triple bond, and they have a pKa of about 25. Now, this is a significant drop in pKa compared to amines, meaning terminal alkynes are much stronger acids. Their conjugate bases are still strong bases, but they're more stable than amide ions. We then enter the range of functional groups with more moderate acidity. Esters also have a pKa of around 25, meaning they exhibit similar acidity to alkynes. Their conjugate bases are resonance stabilized, but still reactive. Next up, we have ketones and aldehydes. They exhibit slightly greater acidity, with aldehydes having pKa values ranging from 17 to 20, and ketones ranging from 20 to 24. The increased acidity is due to the resonance stabilization of their conjugate base. Then as we move lower in pKa, we reach alcohols with a pKa of about 17. Alcohols are significantly more acidic than amines or alkanes. Water is next up with a pKa of 16. This is pretty close in acidity to alcohols. Then we have carboxylic acids. These are much stronger acids than alcohols and ketones with a pKa of around 4. This substantial increase in acidity is due to the resonance stabilization of the carboxylate ion, which makes it a far more stable ion. This is why carboxylic acids readily donate protons in aqueous solution. Finally, at the lowest end of our pKa scale, we have the hydronium ion with a pKa of negative 1.7. This makes it a very strong acid, and that means its conjugate base, water, is extremely weak. In summary, we can see that stronger acids have lower pKa values because their conjugate bases are more stable. On the other hand, weaker acids have higher pKa values because their conjugate bases are highly reactive and unstable. Now that we have covered acids and bases thoroughly, we can move on to another key concept in organic chemistry: nucleophiles, electrophiles, and leaving groups. These species play fundamental roles in reaction mechanisms, particularly in substitution and addition reactions. Let's start with nucleophiles, which are defined as nucleus-loving species. Nucleophiles have either lone pairs or pi bonds that allow them to donate electron density and form new bonds with electrophiles. Since they provide electrons in a reaction, nucleophiles behave as Lewis bases. Some common examples of nucleophiles include anions like bromide, hydroxide, and cyanide. These species carry a negative charge, meaning they have excess electron density that makes them highly reactive towards electrophiles. Nucleophiles can also include molecules with pi bonds, such as alkenes and alkynes and benzene rings, since the delocalized electrons in their pi systems can be donated to an electrophile. Finally, neutral molecules with lone pairs, such as water, ammonia, and esters, can also act as nucleophiles under the right conditions. However, not all nucleophiles react with the same efficiency. The ability of a nucleophile to donate electrons depends on four major factors. First, charge plays a critical role. Nucleophilicity increases with increasing electron density, meaning negatively charged species are stronger nucleophiles than their neutral counterparts. For example, hydroxide is a stronger nucleophile than water because of its negative charge. Second, electronegativity affects nucleophilicity. As electronegativity increases, nucleophilicity decreases because highly electronegative atoms are less willing to share their electrons. For instance, oxygen is less nucleophilic than nitrogen because oxygen holds onto its electrons more tightly. Third, steric hindrance reduces nucleophilicity. Bulkier nucleophiles have more difficulty accessing the electrophilic center, making them less reactive. And then finally, solvent effects can also have a role or an influence on nucleophilicity. Protic solvents like water and alcohols, they hinder nucleophilicity because they can hydrogen bond to and stabilize nucleophiles, reducing their reactivity. This is particularly relevant for negatively charged nucleophiles like halide ions. Now, this point is worth elaborating on because solvent effects play a very important role in determining nucleophilicity. The type of solvent used in a reaction, whether polar, protic, or polar aprotic, can significantly influence the strength and reactivity of a nucleophile. Polar protic solvents like water, methanol, ammonia, carboxylic acid, they have the ability to form hydrogen bonds. These solvents can interact with negatively charged nucleophiles and surround them with a shell of hydrogen bonded solvent molecules. This solvation then stabilizes the nucleophile and effectively reduces its ability to then attack an electrophile. Because of this, nucleophilicity in polar protic solvents increases down the periodic table. So if we were, for example, looking at the halogen group, our iodine is going to be more of a nucleophile than our bromine ion or bromide ion. And that's going to be more of a nucleophile than our chloride ion. And then our fluoride ion is going to be the weakest nucleophile. This trend occurs because larger anions, like iodide, are less affected by solvation due to their more diffuse electron cloud. In contrast, smaller anions, like fluoride, are going to be strongly solvated, and that's going to make them less nucleophilic in polar protic environments. On the other hand, polar aprotic solvents, such as DMF, dimethyl sulfoxide, or DMSO, and acetone, they lack hydrogen bonding and they do not strongly interact with nucleophiles. This allows nucleophiles to remain unsolvated and free to participate in reactions. In these solvents, nucleophilicity follows the opposite trend. It increases up the periodic table. So here, fluoride is the strongest nucleophile because it remains free, whereas iodide, being large and more polarizable, is less effective as a nucleophile in these conditions. Understanding the impact of solvent choice is super important in predicting reaction outcomes. Many substitution reactions like SN1 and SN2 are highly dependent on whether the reaction is carried out in a protic or aprotic solvent. And by recognizing how solvent interactions affect nucleophilicity, we can better predict which nucleophiles will be most reactive under different conditions. With this in mind, we can now shift our focus to electrophiles. Electrophiles are electron-loving species that either have a full positive charge or a partial positive charge, and that makes them highly reactive toward nucleophiles that donate electron density. The key distinction between electrophilicity and acidity is that electrophilicity is a kinetic property, meaning it describes how readily an electrophile reacts rather than how thermodynamically favorable the reaction is. However, electrophilicity often correlates with acidity because molecules that donate protons also tend to be good electrophiles. In practical terms, electrophiles can be categorized based on their degree of positive charge and polarization. A carbocation, which has an empty p orbital, is an excellent electrophile because it has no electron density to donate, and therefore it's highly reactive towards nucleophiles. A carbonyl carbon is also a strong electrophile, but in this case, the oxygen withdraws electron density, creating a partial positive charge on the carbon. This makes carbonyl-containing compounds like aldehydes and ketones prime targets for a nucleophilic attack. Another important factor in electrophilicity is the presence of a leaving group. A molecule with a good leaving group is going to be more likely to undergo a substitution reaction because the bond can break easily and it allows for nucleophilic attack. For example, alkyl halides are good electrophiles because halides are stable after leaving. On the other hand, species like alcohols or amines are weaker electrophiles because their leaving groups are less stable, and that makes substitution reactions less favorable. Again, electrophilicity and acidity are also closely related when ranking carboxylic acid derivatives. So among these, anhydrides are the most electrophilic because they have two electron withdrawing carbonyl groups. That's followed by carboxylic acids and esters, and then amides, which are the least electrophilic due to the electron donating nature of the nitrogen. Now, this is a concept we will revisit in much more detail in a later chapter. Now that we've established the roles of nucleophiles, electrophiles, and leaving groups, we can move on to nucleophilic substitution reactions where these species interact directly. These reactions serve as key examples of nucleophile-electrophile interactions. In both SN1 and SN2 mechanisms, a nucleophile forms a bond with a substrate carbon while a leaving group departs. Now, before we get into SN1 and SN2 and the remainder of this chapter, I want to make a quick note. In this chapter, we're reviewing a lot of key concepts that we are going to reinforce in the following chapters. So I highly recommend watching this chapter and then returning to it after you've completed the playlist. I think it will make a lot more sense to listen to it twice. One, before you cover chapters 5 through 12, and then after you've covered chapters 5 through 12. Now we can start our story of SN2 reactions. A strong nucleophile that also happens to be a weak base, it's going to meet a nice electrophilic carbon that is attached to a halogen, our leaving group. Now, this is the beginning of a love story. So in this fairy tale, the strong and handsome nucleophile makes a bold move, attacking, or as one might say, hitting on the electrophilic carbon that's bonded to the halogen. After the electrophilic carbon gets hit on by the nucleophile, she decides she wants to dump the halogen, our leaving group, and get with the nucleophile instead. How scandalous. This is a classic case of substitution, where the nucleophile replaces the halogen in a single step. There are no intermediates, just one smooth, one-step reaction. We know this is one step because of the reaction energy diagram. It shows only one transition state, meaning there are no intermediate steps. The nucleophile enters as the leaving group exits, forming a new bond in a single step. This is why SN2 is known as a concerted mechanism, where bond formation and bond breaking occur simultaneously. Now, examples of strong nucleophiles that participate in SN2 reactions include halide ions, so Br minus, Cl minus, I minus. Also, alkoxide ions, so Ro minus, and phthalates, Rs minus. These nucleophiles are strong enough to attack, but weak enough that they do not compete too much with elimination reactions. Another important factor in this love story is the type of carbon that the leaving group is attached to. Not all carbons are equally available for SN2 reactions. The nucleophile, first and foremost, must approach from the opposite side of the leaving group, which we call a backside attack. If the carbon is too sterically hindered, meaning it has too many bulky groups surrounding it, the nucleophile is going to struggle to get close enough to attack. This is why SN2 reactions only work well on primary and secondary carbons. A primary carbon is a carbon bonded to only one other carbon and mostly hydrogen atoms, and that makes it very accessible for nucleophilic attack. A secondary carbon is bonded to two other carbons. This makes the attack possible, but slightly hindered. And then for tertiary carbons that are bonded to three other atoms, SN2 is practically impossible due to the excessive steric hindrance. So when you're considering SN2 reactions, primary carbons are ideal, secondary carbons are possible, and tertiary carbons will not react via SN2 because the nucleophile simply cannot reach the carbon due to the bulk of the surrounding groups. Now you might be wondering, why is this reaction called SN2? The name actually gives us key information about the mechanism. S stands for substitution because one group is replacing another. N stands for nucleophilic, indicating that a nucleophile is responsible for the substitution. And 2 here refers to the fact that this reaction is bimolecular, meaning that the rate determining step depends on 2 reactants, the nucleophile and the electrophilic carbon attached to the leaving group. Since the reaction depends on both species, the rate law is written in this manner. This tells us that increasing the concentration of either the alkyl halide or the nucleophile will increase the reaction rate. Lastly, SN2 reactions have one defining feature. They result in an inversion of stereochemistry. Since the nucleophile has to attack from the opposite side of the leaving group, the product will have a flipped configuration at the reaction site. So for example, if the electrophilic carbon has an R configuration to start off with, after SN2 reaction, that carbon will have an S configuration. So to summarize, SN2 is a one-step reaction where a strong nucleophile displaces a leaving group through a backside attack. It favors primary and secondary carbons. The reaction is bimolecular, meaning the rate depends on both the nucleophile and the electrophilic carbon, and it always results in an inversion of stereochemistry. Now that we've told the story of SN2, let's move on to SN1. While SN2 was a direct substitution with a backside attack, SN1 takes a more stepwise approach. Think of it as a love story where the halogen leaves first and only later does the nucleophile come in to take its place. So again, this process begins when the leaving group departs on its own, breaking its bond with the carbon and forming a carbocation. This is a highly reactive, positively charged species. Unlike SN2, where the nucleophile aggressively attacked the electrophilic carbon, SN1 waits for the carbon to become available before the nucleophile steps in and hits on that electrophilic carbon. Before the leaving group departs first, the nucleophile doesn't play a role in the rate determining step. This is why SN1 is known as a unimolecular substitution reaction, where the rate of the reaction depends only on the alkyl halide, not the nucleophile. So the rate law for SN1 is expressed in this way, meaning that increasing the concentration of the nucleophile does not speed up the reaction. Instead, it is the formation of the carbocation that determines how quickly the reaction proceeds. Since forming a carbocation is required, this reaction is favored by substrates that generate a stable carbocation. Tertiary carbons, like the one you see here, are the most favorable for SN1 because they're surrounded by 3 alkyl groups that donate electron density and help stabilize the positive charge. Secondary carbons are less stable, but the reaction can still occur under the right conditions. Primary carbons, however, are highly unstable and they do not undergo SN1 because they lack the necessary stabilization for carbocation formation. Further, looking at the reaction energy diagram, we can see that SN1 has multiple steps. The first peak represents the formation of the carbocation, which is the rate-determining step and the slowest part of the reaction. The second peak represents the nucleophilic attack, which happens much more quickly once the carbocation is available. Because of these distinct steps, the energy diagram for SN1 features 2 transition states, unlike the single transition state that we saw with SN2. Once the carbocation is formed, the nucleophile finally makes its move, attacking the positively charged carbon. This step is much faster than the first because the nucleophile is simply filling the open spot left by the departing halogen. However, there's one unique consideration with SN1, and that is carbocation rearrangements. Carbocations are highly unstable, so if there's a way to become more stable, they will rearrange before reacting with the nucleophile. This often happens through hydride shifts, where a hydrogen moves with its bonding electrons, or through alkyl shifts, where a methyl or a larger alkyl group move to relocate the carbocation to a more stable position. If a secondary carbocation can shift to a more stable tertiary position, it will rearrange before reacting with the nucleophile. This means that the final product of the SN1 reaction might not always form at the original carbon where the leaving group was attached. Let's look at an example. Let's start with the following molecule that's going to undergo SN1 reaction. So our first step is that the bromine leaves. So we form a carbocation at this position. This is a secondary carbocation. Now, you might have your nucleophile come in and attack right here and form the following product. However, the dominant product is going to look a little different. What's going to happen here is something called a hydride shift. There's a hydrogen right here that's going to move to this position. When it does that, this is no longer a carbocation here. The carbocation now moves to the tertiary position because of that hydride shift. So then our nucleophile can come in and attack this position to form the following product. So again, notice, because of this hydride shift, the final product, the dominant product of the SN1 reaction might not always form at the original carbon where the leaving group was attached. Finally, just like with SN2, the name SN1 gives us insight into its mechanism. S stands for substitution, N stands for nucleophilic, indicating a nucleophile is involved, and the 1 stands for unimolecular, meaning that the rate-determining step depends on only one molecule, the alkyl halide, and not the nucleophile. With that, we've completed objective 2. We can now move into objective 3, but we're going to end the video here and pick right up in the next video. I hope this has been helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.